So we're going to talk about one of the most important distributions in statistics, the normal distribution, which also can be called Gaussian distribution. So what you see here is the graph for said distribution, and you can see it's a bell-shaped curve. It is a continuous distribution, meaning that it can take any value within the range, like for example between 1 and 2, like 1.1, 1.3. And you see it's not just a whole number like we saw with binomial or hypergeometric. So, why is the normal distribution so important? Because it shows up everywhere, like in a quality control and other measurements error. So basically a lot of real world situation from this pattern. It's also the foundation for many statistical methods we use today. Second, it's perfectly symmetrical. If you draw the vertical line down the middle at the mean, the left side is a mirror image of the right side. So this means that the mean, median, and mode are all at the same point right in the center. So as we mentioned, the highest point of the curve is at the mean. We're just gonna call its default name mean here. This is where most of the data clusters. As you move away from the mean in either direction, the curve gets lower, meaning fewer observations fall in those areas. Now you see these numbers here. There's a famous rule for normal distribution called the empirical rule or 68, 95, 99 rule. So about 98% of all observations fall within one standard deviation of the mean, that's between here and here, and about 95% fall within two standard deviation of the mean, and 99.7%, essentially almost all the data falls within 3 standard deviation of the mean. But why these specific numbers? This percentage comes from the mathematical properties of the normal distribution curve. So when you calculate the area under the curve, which represent the proportion of data, you get about this percentage as we seen here. It gives you a quick way to understand the spread of data in a normal distribution without doing complex calculations. So in short, if you know the mean and standard deviation, you immediately know where most of your data falls. So let us look at a real world example using the same graph. Height of adult male roughly follow the normal distribution. By the way, this data isn't accurate. It's just an example. So let's say most men are around the average height of 170 centimeter. That's the peak of the curve. Some are shorter here and some are taller, but extremely short or extremely tall men are rare. Those are in the tails of the distribution. Another example is the exam scores in a large class. Large class often follow a normal distribution. Most students score around the average. Let's say the average is in this school is around 70% score. Fewer get very high or very low scores, and certainly students that get exactly 0 or 100 are extremely low, which will end up in these entails. So remember the key feature of normal distribution. The bell-shaped curve, symmetrical around the mean, median, and mode are all equal and at the center, spread measured by standard deviation, and most data within a few standard deviation of the mean. Next, we look at the following normal distribution formulas, started with probability density function. So a continuous random variable x follows a normal distribution has this probability density function. It looks complicated, and it certainly is. Integrating this function to find probability is mathematical very difficult. So the function depends on two parameters, which are the mean and the variance, or equally the standard deviation, and rewrite this as x follows n of mu, mean, and standard deviation. And variance. So the problem with this is that every different normal distribution with different mean and different standard deviation will require separate calculation and different probability tables. If one data set has, let's say, mean 50 and standard deviation 10, another has mean 100 and standard deviation 5, we need a different table for each, which is extremely impractical. So what do we do about it? We convert any normal distribution into what we call a standard normal distribution. This standard normal distribution is a special normal distribution that always has mean equals to 0 and variance or standard deviation equals to 1. Thus, the transformation from this formula, where the z is a random variable for standard normal distribution denoted by z follows n 0, 1. This is the table for the z-score table. There are other kinds of table for the z-score, but we will only be using for this curve to the right of z, as this is the exercise. This is the table we will be using for our exercise throughout the whole statistic exercise in the future. So in conclusion, the Z transformation standardize any normal distribution into standard normal distribution like we said before, with mean equals to 0 and variance equals to 1. This makes calculation much easier and allows us to use a single reference table, which is this one, for all normal distribution problems. To understand this better, I highly suggest to go watch this video, as they make it very easy to understand about standard normal distribution. And I'll give the link to it as well in the description. So all those explanations can be confusing, so let's just start applying them. We look at exercise 1, nothing too complicated, very straightforward in fact, just to familiarize ourselves with normal distribution. So the question, the weight of a power transformer used in industrial applications is normally distributed with a mean of 45 kg and a standard deviation of 6 kg. What is the probability that a randomly selected transformer weighs, for let's start with A, at least 54 kg? Firstly, we extract required information from the question. Normally distributed with a mean of 45 kg. So here it's already stated that it's a normal distribution and it gives us a mean equals to 45. Next, standard deviation of 6 kg. So standard deviation is 6. Reminder not to be confused with variance. This is variance and this is standard deviation. I put in SD. So with this mean and standard deviation, we can now solve the question. It wants the probability at least 45 kg. So this is for at least. So using the standard normal distribution formula, insert the mean and standard deviation values and we get 1.5. So next, we need to refer to the z-score table, and since this graph shows at least 1.5, meaning it's on the right side of normal distribution. this graph looks exactly, okay, looks exactly like this table, so no need to think further and just use the table as is. So according to the table, 1.50 is 0.0668. So the final answer is 0.0668. On to the next question. B is less than 54 kg. So the probability less than 54 is here, like this one. We solve the same like in A, mean and standard deviation stays the same. And we get P less than 1.5. So here is a bit different than A, since less than 1.5 will end up looking like this. And our z-score table only apply for this part. So what we do, we simply 1 minus z more than or equals 1.5. So solve it. 1.5 from z table is 0.00668 and the final answer is 0.9332. Next question, C is at most 39 kg. At most means less than or equals 39. Solve it like usual and we get the probability z less than or equals -1. So the standard normal distribution according to this will look like this. So keep in mind when it comes to the negative on the left side, according to the theory on what we learned, this graph is perfectly symmetrical. So that means this z less than or equals -1 is the same as more than or equals 1. Now we can solve it using z table. So the final answer is 0.1587. Finally, D is between 39 and 54 kg. So this is for between. Solve it and we get probability z between -1 and 1.5. And if we graph it, then this is the result. We already gotten the result for this both area in our previous question. So to get the middle, we 1 minus those two sides. And final answer is 0.7745. That's all for the basics. And now let's dive into a bit more challenging question. Exercise 2. Print circuit boards PCBs manufactured at a facility have weights that are normally distributed with a mean weight of 85 gram and a standard deviation of 8 gram. A PCB is selected at random. So we start with question 1. What is the probability that the weight of PCB lies between 71 gram and 97 gram? So we just solve similar question from the exercise 1. So that means, well, the in between here, the probability is between x 71 and 97. So from the question, we know that the mean value is 85 gram and the standard deviation is 8. So back to it like this. So we insert the values into the equation and we get z is between -1.75 and 1.5. Graph it and it should look like this one. So let's find the area on both of these sides. The right side is straightforward as it means Z is more than or equal, honestly, it doesn't really matter if it's more than or equal, as normal distribution is continuous. So on the left side, like we learned in exercise 1, the negative on the left side is the same as the right side. So basically, it's mirror each other. So here, like this, now we can solve it. So using the Z table, negative 1.75 is 0.0401 and 1.5 is 0.0668. So the final answer is 0.8931. Next question 2 is, what is the probability that the weight of PCB is more than 105 gram? This is easier than the last. So more than 105. Solve the equation and we get Z more than 2.5. This is its graph. We can straightforward use the Z table. Also, a reminder again that more than and more or equal then can be solved the same way in normal distribution as it is continuous. So moving on, from Z table, 2.5 is 0.0062. Question 3, if 12% of the PCBs produced are considered heavy, what is the minimum weight of PCBs in that category? So here, unlike what we solved before, the question wants us to find weight. It already gives us the info for the probability, which is 12%. So let's just write out what we know. Since we don't know the weight, let's assume it's A, and the probability given is 12% or 0.12. Insert the mean and standard deviation value. So things to know that this one here also means Z alpha. There's actually another table for these topics, and it is for critical values for normal distribution. This is the table. Now compare it to Z-score table here. The one we always use is for when trying to find probability here, and it gives us weight like what we did in our previous exercise. But here, it's the opposite. It is from when we already know our probability values, alpha, and it asks us for weight. There are other scenarios, but I'm using the example uses in this exercise. So with that, let's find our probability. So it gives us 12% or 0.12. So our Z alpha is 1.1750. So here, with that, we have all the values. So now, just find A. So final answer, the minimum weight of PCB is 94.4 gram. This question is a bit challenging, but at the end, it all comes down to applying basic maths and logic. Lastly, final question. It's the same as question 3, but there's a slight twist to it. If 60% of the PCBs produced weight above a certain threshold, what is the minimum weight threshold? So up to this point, it's exactly like question 3, but with our probability is 60% or 0.6. So people usually stumble here as they assume that 0.6 or 60% located here in the graph, which is wrong. This is due to the lack of understanding about normal distribution. So let's look back to it. You see the percentage here? If we total it all, it will become 50% on this side. The same as the left side as it is symmetrical. So both makes it 100% or probability 1. So each sides only make up 50% or 0.5 probability. With that in mind, 0.6 here doesn't make sense. So the graph should look like this. Like this one. So the half takes 0.5 and continues with 0.1 on the left side. Obviously, we can find our values from the Z table with this. So we be taking this side instead. So 1 minus 0.6 equals 0.4. So change it and solve it like usual. 0.4 will be 0.2533 from the table. But you must include negative as accordance to the graph here as it's on the left side. So the final answer for the minimum weight is 82.9736 gram. Anyways, that's all for normal distribution. Thank you.